In 2025, 4 astronauts will face the most dangerous moment of modern space exploration. Not the launch, not the journey to the moon, the return. Because after 50 years of technological progress, we still don't know how to perfectly control what happens when a capsule hits the atmosphere at 25,000 miles per hour. Artemis 2 will be the first crewed mission to test a technique never used in lunar return: skip entry. 2 dips into the atmosphere, 2 encounters with plasma, 2 chances for something to go wrong. The heat shield will disappear by design, carrying heat away as it burns, but the erosion pattern will be different from any test. Different from Artemis I, different from any simulation. This is the story of why coming home is harder than leaving, and why, after half a century, physics still hasn't promised us complete control over the most violent moment of the journey. Reentry from lunar distance is not a procedure. It's an encounter. The Orion capsule will strike the upper atmosphere at 25,000 miles per hour, compressing air into plasma, temperatures exceeding 5,000 degrees Fahrenheit, hot enough to vaporize steel in seconds. Protection depends on a heat shield designed to disappear. Material ablates, carrying heat away as it burns. The shield doesn't resist the event, it sacrifices itself to it. And here's the problem. Every reentry is different. Atmospheric density fluctuates. Entry angles vary by fractions of a degree. Models predict what should happen, but physics doesn't promise exact repetition. And that uncertainty begins with speed. 25,000 miles per hour. That's the speed Artemis 2 will carry when it re-enters Earth's atmosphere. Roughly 32 times the speed of sound. Fast enough to cross the continental United States in 6 minutes. At that velocity, air doesn't behave like air anymore. The capsule doesn't push through the atmosphere, it compresses it. Molecules can't move out of the way fast enough. They pile up in front of the vehicle, creating a shock wave that heats gas into plasma. This isn't friction in any ordinary sense. It's kinetic energy converting directly into thermal energy. Every second of motion becomes heat, and heat, at this scale, becomes a problem that materials barely survive. Apollo capsules faced the same physics. In 1969, Apollo 11 returned at similar speeds. The heat shield charred, cracked, and eroded as designed. Armstrong, Aldrin, and Collins survived because the ablation happened within acceptable limits. Acceptable. Not perfect. Not controlled. Acceptable. 50 years later, Orion uses different materials, AVCODE instead of the older ablative compounds. More refined, better tested in simulations. But simulations don't reproduce the full convergence of speed, angle, atmospheric variation, and real-time material response. No wind tunnel on Earth can replicate 25,000 miles per hour through transitioning atmosphere. No lab can perfectly model plasma chemistry as it fluctuates across a 5-meter heat shield over 20 minutes of descent. The phenomenon exists only when it's actually happening. You can't rehearse it. You can only survive it. And survival depends on the vehicle staying within a corridor of acceptable heating. Too steep, and thermal load exceeds material limits. Too shallow, and the capsule skips off the atmosphere back into space, or burns up during prolonged exposure. The corridor is narrow. Fractions of a degree separate survival from failure. Artemis 2 will aim for the center of that corridor. But the center is a range, not a point, and the vehicle must pass through it while traveling faster than any human has moved in 50 years. Control, at this scale, becomes negotiation with physics that won't compromise. And that negotiation depends entirely on a shield designed to destroy itself. The Orion heat shield is 5 meters wide, the largest ever built for human spaceflight. It weighs over 2,000 kilograms, 16 blocks of ablative material bonded to a titanium skeleton, engineered with precision measured in millimeters. And it's designed to be destroyed. Ablation is not damage, it's function. The shield doesn't resist heat. It absorbs it and departs with it. Material heats, melts, vaporizes, and carries thermal energy away from the structure. Protection happens through controlled disappearance. In theory, this process follows predictable patterns. Engineers calculate how much material will erode under expected thermal loads. They design margins, extra thickness, to account for variation. In practice, erosion doesn't trace smooth boundaries. Apollo heat shields returned with asymmetric charring. Some areas ablated more than predicted, others less. The pattern emerged only after the event, reconstructed from what remained. Orion's shield has been tested in arc jets, facilities that simulate reentry heating by blasting samples with superheated plasma. The tests validate material performance under controlled conditions. But no arc jet reproduces the full dynamic environment. Temperature varies across the shield surface. Plasma chemistry shifts as altitude changes. Microscopic cracks propagate in ways models approximate, but don't fully predict. The shield will work. It has to. But work means eroding within acceptable limits, not eroding perfectly. During Artemis I, the uncrewed test flight, in 2022, Orion's heat shield performed as expected. But post-flight analysis found more char loss than models anticipated in certain areas. Not enough to threaten the mission, just enough to show that reality diverges from simulation in ways that matter. The differences were small, but at 5,000 degrees, small differences scale. Artemis II will carry 4 humans through the same event, same physics, same material, same unpredictability. The shield will protect them by disappearing in a pattern that won't be identical to Artemis I, or to any test, or to any future mission. Each reentry writes its own history into the material. Once, irreversibly, and then the shield is gone. But Artemis II won't use the same reentry profile Apollo did. It will attempt something no crew has ever survived before. Artemis II won't descend straight down. Instead, it will use a technique called skip entry, dipping into the atmosphere, lifting back out, then descending again. Like a stone skipping across water, but at hypersonic speed through transitioning air. Apollo didn't do this. Apollo capsules entered once, descended continuously, and splashed down. Simple, direct, proven across 6 crewed lunar missions. Orion uses skip entry because it offers advantages. The technique spreads heating over a longer duration, reducing peak thermal load. It extends the range of possible landing sites, giving mission control flexibility if weather shifts or recovery assets move. It also introduces variables that Apollo never encountered. The first atmospheric pass generates plasma, heats the shield, and begins ablation. Then the capsule lifts back into near vacuum, where thermal conditions shift abruptly. Material that was ablating milliseconds earlier now faces cold, rarefied air. Then it dips again. Heat returns. Plasma reforms. Ablation continues, but from a surface already altered by the first pass. No human crew has ever experienced skip entry from lunar return velocities. Artemis, I demonstrated the profile worked with an empty capsule. Sensors recorded temperature, acceleration, and plasma density. Data looked good. But good means within expected ranges. Not identical to prediction. Not free of variation. Just survivable. The problem is that skip entry multiplies the opportunities for small divergences to accumulate. 2 atmospheric passes mean 2 chances for angle, density, or material response to deviate slightly. 2 transitions between heating and cooling. 2 moments where models confront reality and discover they were approximate. Engineers account for this with margins. The heat shield is thicker than minimum requirements. Entry angles are chosen conservatively. Guidance systems adjust in real time based on sensor data. But real-time adjustment depends on sensors that are themselves being ablated. Instrumentation embedded in the shield will char, erode, and fail as the material disappears. Data will arrive from a system that is actively being consumed by the event it's trying to measure. Artemis 2 will be the first crude test of skip entry from deep space. It's not untested. It's tested once, on an empty capsule, under conditions that won't repeat exactly. And the difference between tested once and fully understood is the difference between confidence and certainty. We have confidence. We don't have certainty. This uncertainty isn't new. It's existed for 50 years. We've just gotten better at accepting it. 53 years separate Apollo 17 from Artemis 2. In that time, computing power increased by a factor of 10 million. Materials science advanced. Simulations became detailed enough to model plasma flow at molecular scales. Spacecraft design evolved from slide rules to supercomputers. But the physics didn't change. 25,000 miles per hour still converts into 5,000 degrees Fahrenheit. Plasma still forms the same way. Ablation still governs survival. The atmosphere still fluctuates in ways models can't perfectly capture. Apollo astronauts returned through this phenomenon 12 times. Every mission succeeded. Every crew survived. But survival came with variation. Apollo 10's heat shield charred unevenly. Apollo 12 experienced higher heating than predicted due to a steeper entry angle. Apollo 15's capsule landed further off target than expected because atmospheric density differed from forecasts. Not failures, just reminders that the event resists total predictability. The technology improved, but the fundamental uncertainty persisted. Gene Cernan, the last human to return from the moon in 1972, described reentry as riding a meteorite. Not piloting, not controlling, riding. 50 years later, Orion offers more capability than Apollo in almost every metric. More power, more redundancy, better guidance, advanced materials. Yet the capsule still depends on ablation, material disappearing under conditions that can't be fully rehearsed. It still navigates a corridor measured in fractions of a degree. It still encounters plasma that behaves slightly differently every time. Progress didn't eliminate the problem. It refined the approach to the problem. And refinement is not the same as mastery. The Artemis 2 crew will experience what no living astronaut has felt since 1972. They'll accelerate toward Earth faster than any human currently alive has ever moved. They'll be surrounded by plasma hotter than anything on the planet's surface. They'll depend on a shield designed to self-destruct in a controlled pattern. And they'll do this knowing that every previous reentry, Apollo, Soyuz, Orion, Uncrewed, encountered variations that models didn't fully anticipate. Not catastrophic variations, just enough to show that nature doesn't repeat itself with precision. The universe doesn't promise reproducibility. It promises physics, and physics at this scale allows for margins, but not guarantees. 50 years of progress gave us better tools. It didn't give us control over what happens when matter meets energy at the edge of survivability. And the gap between our tools and complete understanding shows up every time we compare prediction to reality. Computer models can simulate reentry in extraordinary detail. They solve equations governing fluid dynamics, thermodynamics, and material science. They predict temperature at thousands of points across the heat shield. They calculate ablation rates, plasma chemistry, and shock wave formation. The simulations are accurate enough to guide design, accurate enough to set mission parameters, accurate enough to give confidence, but not accurate enough to eliminate surprise. During Artemis I, sensors measured unexpected turbulence in the plasma wake. Not dangerous, just different from what models predicted. The capsule handled it. The heat shield performed, but the data showed that reality included phenomena the simulations missed. This isn't a failure of modeling. It's a structural limit of what models can do. Reentry involves coupling between processes that evolve on different timescales. Plasma chemistry changes in microseconds. Heat conducts through material in milliseconds. The capsule's trajectory shifts over seconds. Atmospheric density varies across kilometers. Models divide these processes into discrete steps. They approximate interactions. They assume certain variables remain stable within bounded ranges. But real atmospheric reentry doesn't step through discrete stages. It flows continuously. Variables interact in real time, creating feedback loops that simulations handle through approximation. Approximation works, but approximation is not replication. The gap between simulation and reality shows up in post-flight data. Engineers compare what sensors recorded to what models predicted. The curves overlap, but they don't align perfectly. Peaks appear at slightly different times. Temperatures diverge by tens of degrees. Ablation patterns show asymmetries that weren't forecasted. These differences are small enough to stay within safety margins. That's the point of margins, to accommodate variation. But margins are admission of incomplete knowledge. They're buffers against the irreducible uncertainty of encountering a phenomenon that resists perfect prediction. Artemis II will generate new data, temperature readings, acceleration profiles, plasma density measurements, material erosion patterns. Some will match predictions closely, some won't. Engineers will analyze the divergences, refine the models, and prepare for Artemis III. But refinement doesn't converge to perfection. It converges to better approximation. And better approximation still means that the next reentry, like every reentry before it, will encounter conditions that weren't fully anticipated. The phenomenon is understood, but understanding, here, means knowing what can happen, not knowing exactly what will happen. There's a difference, and the difference is where uncertainty lives. But perhaps the deepest uncertainty is this: no one will actually see what happens. No one has ever seen reentry from outside while it's happening. Not at lunar return velocities. Not with human eyes. The plasma envelope that forms around the capsule is opaque. Communication cuts off. Radio signals can't penetrate the ionized sheath. For several minutes, the crew was isolated inside a glowing barrier that no observer can see through. Cameras on the ground might capture a bright streak across the sky. If the entry happens over populated areas, in daylight, with clear weather, but the streak reveals nothing about what's occurring inside the plasma. Sensors record data. Accelerometers measure g-forces. Thermocouples track temperature. But sensors don't witness. They sample discrete points and transmit numbers. The crew feels it. They experience deceleration pressing them into their seats. They might glimpse orange light through the windows, plasma glow leaking past the heat shield's edges. They hear nothing, because sound doesn't travel the same way through ionized gas. But they can't see the shield ablating. They can't observe the plasma flowing around the capsule. They can't watch the material eroding away to protect them. The phenomenon surrounds them completely, and they are inside it, unable to witness what's saving their lives. But Artemis 2 will capture something unprecedented. For the first time in history, we'll have high-resolution data from inside the plasma during skip entry from lunar velocities, temperature readings from a shield being consumed by fire it helped create, acceleration profiles from a capsule dipping twice into an atmosphere that wasn't designed to be entered this way, data from sensors that are themselves being destroyed as they record, a testimony from instruments that won't survive to be read twice. Apollo astronauts described Reentry as the most physically intense experience of the mission, more violent than launch, more disorienting than microgravity, a return to gravity that felt less like homecoming and more like collision. Gene Cernan said it was like being inside a meteor. Jim Lovell, who flew to the moon twice, called it a controlled crash, not piloted, not steered, just endured. The Artemis 2 crew will experience the same thing. For humans inside a capsule, surrounded by plasma they can't see, protected by material they can't observe disappearing, descending through an event that happens too fast and too violently for real-time comprehension. They'll trust the heat shield. They'll trust the guidance system. They'll trust 50 years of engineering that refined the process without eliminating its fundamental character. And when the plasma clears, when communication returns, when parachutes deploy and the capsule drifts toward the ocean, only then will they know that it worked. Not because they controlled it, because they survived it. The universe doesn't provide witnesses to its most extreme transitions. It provides survivors. And survival is not the same as understanding, which brings us to the question this mission can't answer. Artemis 2 will send humans farther than anyone alive has traveled. It will validate technology that didn't exist during Apollo. It will test systems designed with 5 decades of advancement. It will mark humanity's return to deep space exploration after the longest gap in the history of spaceflight. But the mission's success will ultimately depend on passage through a phenomenon we still can't perfectly predict. Re-entry from lunar distance remains an encounter with physics that won't compromise. The capsule will hit the atmosphere at 25,000 miles per hour. Plasma will form. The heat shield will ablate, and the process will unfold slightly differently than it did during Artemis I, slightly differently than any simulation, slightly differently than it ever has before. 50 years of progress gave us better materials, more computing power, refined models. It didn't give us control over what happens when velocity becomes heat at the edge of survivability. We're better at going to the moon than we are at coming home. Not because the return is harder in an absolute sense, but because departure is reproducible and return is not. Every launch follows the same physics. Every re-entry encounters the same physics, but never quite the same way. The question Artemis 2 raises is not whether the crew will survive. They will. The margins are sufficient. The engineering is sound. The question is what it means to expand into space, while depending on tolerance, rather than mastery at the moment of return. What does it mean to reach farther, knowing the hardest part is getting back? And if we still don't fully understand the passage home after 50 years of trying, what does home even mean when you're traveling at 25,000 miles per hour through plasma you can't control? The journey continues. The uncertainty remains. More questions waiting. If this changed how you see what it means to return, consider subscribing. There are more questions waiting.